Most of what we call the ocean has never been seen by human eyes, not because it's hidden or forbidden, but because it exists in a form of darkness that predates human observation entirely. The ocean you imagine when you think of water, the one that moves with light and color and visible life, represents only the thinnest surface layer. Below that, for hours of falling, is something else. Not mysterious in the theatrical sense, but simply beyond the reach of the senses we use to confirm that a place is real. When we speak of ocean depth, we are mostly speaking about the limits of where light can go and what remains when it cannot. The surface of the ocean is not a fixed thing. It changes shape constantly, responsive to wind and temperature, and the gravitational pull of the moon. And yet for all that motion, it remains the boundary where two substances meet and refuse to mix completely. Air and water press against each other here, exchanging heat and gas and energy, and the result is a thin band of illumination where photosynthesis becomes possible and color still functions as a meaningful category. This is the layer you can see from a boat or a beach, the part that reflects sky and absorbs sunlight and supports the forms of life that depend on both. It is also the only part of the ocean that behaves in ways human senses evolved to interpret. Below this band, the rules begin to shift, not suddenly, but in increments so gradual that no single moment marks the transition. The ocean does not announce where it stops being familiar. It simply continues downward, and the conditions that make observation possible begin to thin. Light penetrates seawater according to principles that are well understood but difficult to experience directly. When sunlight strikes the surface, it enters as a spectrum, a mixture of wavelengths that together produce what we perceive as white light. But water is not a neutral medium. It absorbs certain wavelengths more readily than others, filtering the spectrum as light moves deeper. Red light is absorbed first, within the top few meters, so that anything red in color, blood, coral, certain fish, begins to lose its appearance almost immediately beneath the surface. Orange follows, then yellow, until only the shorter wavelengths remain. Green light can penetrate further, and blue light further still, which is why the deeper parts of the illuminated ocean often appear as gradations of blue-green, a color palette that narrows as depth increases. This is not a poetic observation, but a consequence of physics, the interaction between electromagnetic radiation and the molecular structure of water. The ocean does not choose to be blue. It simply absorbs every other possibility first. At around 200 meters, most of the sunlight that entered the surface has been absorbed or scattered. What remains is faint, diffuse, insufficient for photosynthesis, but still detectable to eyes that have adapted specifically for low light conditions. Many species of fish and cephalopods live in this transitional band, where vision still operates, but color has largely ceased to exist as a useful distinction. Their world is one of contrasts and silhouettes, of shapes defined against a dimming background rather than by hue or saturation. It is a zone where seeing becomes less about detail and more about detecting movement or the faint bioluminescent signals that some organisms produce to communicate or hunt. The light here is not darkness, not yet, but it is no longer the kind of light that would feel recognizable to a creature evolved on land. It is light at the edge of its utility, still present but no longer dominant. By 300 meters, the reduction becomes more absolute. The amount of sunlight reaching this depth is less than 1% of what struck the surface, and it arrives so weakened that it no longer influences temperature or chemistry in meaningful ways. The ocean here begins to feel less like an extension of the sunlit world and more like a separate system, one that operates according to principles unrelated to the presence or absence of daylight. Temperature drops. Pressure increases. The organisms that live here do not depend on the sun's energy directly, but instead rely on the slow descent of organic matter from above, dead plankton, fecal pellets, fragments of larger creatures, all of it drifting downward in a continuous, invisible rain. This is called marine snow, and it represents the primary energy source for most of the deep ocean. It falls constantly, silently, accumulating in layers or being consumed before it reaches the bottom. The deeper you go, the less of it there is, because it gets intercepted and digested along the way. The ocean's food supply, like its light, diminishes with depth. At around 600 meters, sunlight ceases to penetrate in any form that human instruments can measure. This boundary is sometimes called the compensation depth, the point at which the energy a photosynthetic organism can capture from light equals the energy it expends simply to stay alive. Below this line, photosynthesis is not merely difficult, but thermodynamically impossible. The ocean continues for thousands of meters beyond this point, but it does so in complete and permanent darkness. Not the darkness of night, which is temporary and still faintly illuminated by stars or moon, but a darkness that has persisted since the ocean formed, uninterrupted except by the occasional bioluminescent flash or the artificial lights of human submersibles. This is the beginning of what is often called the deep sea, though the term itself is imprecise, a human boundary imposed on a continuum that does not recognize categories. The ocean does not become deep at any specific meter mark. It simply continues, and the conditions continue to change, and at some point the accumulation of those changes makes it clear that you are no longer in the world where light determines what is possible. The transition is not dramatic, but it is total. And once it occurs, the ocean begins to feel less like a variation of the surface environment and more like a distinct realm, one that functions entirely without reference to the sun. Pressure in the ocean increases at a rate that is both predictable and difficult to translate into human experience. For every 10 meters of descent, the pressure increases by approximately 1 atmosphere, which is to say, it increases by the equivalent of all the air pressing down on the Earth's surface at sea level. At 100 meters, you are experiencing 10 times the atmospheric pressure you would feel standing on land. At 1,000 meters, 100 times. The progression is linear and unrelenting, and it means that the deeper regions of the ocean exist under forces that would collapse most structures not specifically designed to withstand them. Human lungs would compress to a fraction of their normal volume. Air-filled spaces would implode. Bones would endure, but soft tissue would deform under the weight of water, pressing inward from all directions at once. And yet organisms live at these depths, not by resisting the pressure, but by never having known anything else. Their bodies contain no air pockets, no rigid cavities that could collapse. Their cells are filled with incompressible fluids, their proteins adapted to function under conditions that would denature the proteins of surface-dwelling creatures. They do not experience the pressure as oppressive because they have no reference point for its absence. It simply is, in the same way that gravity is, a condition of existence rather than an obstacle to it. Temperature in the deep ocean stabilizes at a point far colder than most surface water. Below 1,000 meters, the temperature hovers near 2 degrees Celsius, just above freezing, and remains there with very little variation regardless of season or latitude. This is because the deep ocean is not heated by the sun, but by the slow mixing of water masses that originate in polar regions, where surface water becomes dense enough to sink and spread along the ocean floor. These currents move at speeds measured in centimeters per year, carrying cold water across entire ocean basins in journeys that can take centuries to complete. The result is a thermal uniformity that extends across vast distances, a cold stillness that persists regardless of what happens above. Surface waters may warm or cool with the seasons, may be churned by storms or calmed by windless days, but the deep ocean remains insulated from all of it, locked into a temperature regime that has remained stable for thousands of years. Life here does not experience temperature as a variable. It is a constant like the darkness, like the pressure, and organisms have adapted to it so thoroughly that most of them cannot survive in warmer water even if all other conditions remain favorable. The creatures that inhabit this zone are not abundant in the way surface life is abundant. There are no vast schools of fish, no dense coral reefs, no forests of kelp. Food is scarce, and energy must be conserved. Many deep-sea fish are small, with soft bodies and reduced skeletal structures, their forms shaped by the need to expend as little energy as possible in an environment where the next meal may be days or weeks away. Some have enormous mouths relative to their body size, adaptations that allow them to consume prey larger than themselves when the opportunity arises. Others have evolved bioluminescence, the ability to produce light through chemical reactions within specialized cells, and they use this light in ways that serve multiple purposes, attracting prey, confusing predators, signaling to potential mates. The light they produce is almost always blue or green, wavelengths that travel furthest in water, and it appears as brief flashes or glowing lures rather than continuous illumination. In the absence of sunlight, bioluminescence becomes the primary form of visible communication, a language of flickers and glows that conveys information in an otherwise lightless world. Bioluminescence is common in the deep ocean, far more common than it is on land or in shallow water, and this suggests something about the role light plays, even when it is not present, as a natural environmental feature. Organisms have not abandoned vision in the deep sea. They have repurposed it. Eyes in this zone are often highly sensitive, capable of detecting the faintest emissions, and in some species they have become enlarged to the point where they dominate the head, massive spheres of photoreceptive tissue designed to capture every available photon. Other species have evolved eyes that point upward, watching for the silhouettes of prey or predators passing overhead against the faint residual glow that sometimes filters down from shallower depths. Still others have lost their eyes entirely, relying instead on other senses, chemical detection, vibration sensitivity, electrical field perception, to navigate and hunt. The absence of light does not eliminate the importance of sensing the environment, it simply shifts the methods by which that sensing occurs. The deep sea is not a uniform space but a layered one, divided into zones that marine biologists have named based on depth and the corresponding changes in light, pressure, and temperature. The mesopelagic zone extends from 200 to 1,000 meters, the region where twilight fades into darkness. Below that lies the bathypelagic zone, from 1,000 to 4,000 meters, where darkness is complete and pressure is measured in hundreds of atmospheres. Deeper still is the abyssopelagic zone, from 4,000 to 6,000 meters, and finally the hadal zone, which includes the ocean trenches and extends beyond 6,000 meters to the deepest known points. These divisions are human constructs, ways of organizing a continuum that does not organize itself, but they reflect real changes in the biological and physical character of the ocean. Each zone supports different communities of organisms, different survival strategies, different rates of biological activity. The deeper you descend, the fewer individuals you encounter, the slower metabolisms become, the longer lifespans extend. Life does not disappear with depth, but it becomes more dispersed, more patient, more attuned to waiting. At 4,000 meters, you are deeper than most mountains are tall, and the ocean still continues below you for thousands of meters more. The ocean floor at depths between 4,000 and 6,000 meters is not the dramatic landscape of trenches and ridges that often appears in illustrations. Most of it consists of abyssal plains, vast stretches of seafloor that are among the flatest places on Earth. They extend for hundreds or thousands of kilometers, with slopes so gradual that they are effectively imperceptible, interrupted only occasionally by seamounts or the slow accumulation of sediment into low hills. The sediment itself is fine, composed of the remains of microscopic organisms that lived and died in the sunlit layers above and then drifted downward over weeks or months, settling in a continuous, silent deposition that has been occurring for millions of years. In some areas, the sediment layer is hundreds of meters thick, a geological archive of everything that has fallen from above, compressing slowly under its own weight into rock that will one day be uplifted by tectonic forces and exposed on land as limestone or shale. The process is so slow that it operates outside the scale of human perception. A single centimeter of sediment may represent 1,000 years of accumulation. A meter may represent 100,000. The abyssal plains are landscapes built by time, not by any force that could be observed in a human lifetime. Life on the abyssal plains is sparse but not absent. The seafloor here is inhabited by creatures that move slowly or not at all, their metabolisms tuned to an environment where energy is scarce and opportunities to feed are infrequent. Sea cucumbers crawl across the sediment, ingesting it and extracting whatever organic material it contains, leaving behind trails that mark their passage. Brittle stars extend their arms into the water column, filtering particles from the slow currents that move across the bottom. Polychaete worms burrow into the sediment, constructing tubes from mucus and sediment grains, their bodies hidden except for the feathery feeding structures they extend upward. These organisms are not large or dramatic. Most are small, unobtrusive, adapted to survive on the meager resources that reach the deep sea floor. They do not hunt actively or move quickly. They wait and they process, and they exist in a state that resembles dormancy, except that it is their normal mode of operation. Population densities are low, measured in individuals per square meter rather than per square centimeter, and the distance between one organism and another can be vast relative to their size. They are scattered across the plains like artifacts in a desert, separated by expanses of empty sediment that stretch beyond the range of any light a submersible might cast. Human exploration of the abyssal plains has been limited by the same factors that make them difficult for life: depth, pressure, and distance from the surface. Submersibles capable of reaching these depths are rare and expensive, and the logistical challenges of deploying them mean that each dive represents a significant investment of time and resources. Most of what we know about the abyssal seafloor comes not from direct observation, but from indirect methods: sonar mapping, sediment cores, trawls that scrape the bottom and bring up samples of whatever they encounter. These methods provide data, but they do not provide the kind of immersive understanding that comes from sustained observation. A sonar map can reveal the topography of the seafloor, but it cannot show you what lives there or how those organisms interact. A sediment core can tell you what the bottom is made of, but it cannot convey the experience of being there: the stillness, the cold, the weight of the water pressing down. Even video footage from remotely operated vehicles offers only a narrow slice of visibility, a cone of light moving through darkness, capturing whatever happens to pass within its range during the brief time it is deployed. The abyssal plains exist mostly beyond the reach of human observation, known in outline but not in detail, mapped but not truly seen. The average depth of the ocean is around 3,700 meters, which places it firmly within the abyssal zone. This means that the deep ocean is not an exception or an extreme environment, but the most common type of marine habitat on Earth. The shallow coastal waters where most marine biology has traditionally been studied, the sunlit reefs and kelp forests and tide pools, represent a tiny fraction of the total ocean volume. The vast majority of the ocean is deep, cold, dark, and under high pressure, and it has been that way for as long as the ocean has existed. Surface conditions are the anomaly, not the baseline. And yet human understanding of the ocean has been shaped almost entirely by what we can access easily, which means we have spent centuries studying the exception and treating it as representative of the whole. The deep ocean remained almost entirely unknown until the mid-20th century, and even now, with advanced technology and decades of research, it remains one of the least explored environments on the planet. More people have walked on the moon than have descended to the deepest parts of the ocean. More of the Martian surface has been mapped in high resolution than the Earth's seafloor. This is not because the deep ocean is inherently more difficult to study than outer space, though the challenges are considerable. It is partly a matter of perception and priority. Space exploration captures the imagination in ways that ocean exploration often does not, perhaps because space is associated with discovery and expansion, while the ocean is associated with what is already known, even when it is not. The ocean is familiar in the sense that it is visible from shore, accessible to swimmers and sailors, a part of everyday experience for much of human history. But the deep ocean is not familiar in any meaningful way. It is as remote and alien as any planetary surface, governed by physical laws we understand in principle, but rarely encounter in practice, inhabited by organisms that look and function in ways that seem disconnected from the biology of the surface world. And yet it occupies the same planet, exists beneath the same water that laps against beaches and harbors, separated from the human world not by distance measured in light years, but by a vertical descent of a few thousand meters. The abyssal plains stretch outward in all directions, covering more of the Earth's surface than all the continents combined, and almost all of it remains as it has always been, untouched and unwitnessed. Sound travels differently in water than it does in air, and this difference becomes more pronounced as depth increases. In air, sound moves at roughly 340 meters per second, and it dissipates quickly, absorbed by distance and interference. In water, sound travels more than 4 times faster, at around 1,500 meters per second, and it can propagate over distances measured in hundreds or even thousands of kilometers under the right conditions. This is because water is denser than air and more efficient at transmitting mechanical vibrations. The ocean, despite its vastness, is not a silent place. It is filled with sound, biological, geological, human-made, that travels through the water in ways that make it the primary sensory channel for organisms that cannot rely on vision. Marine mammals use sound to navigate, to hunt, to communicate across distances that would be impossible to bridge by sight. Whales produce low-frequency calls that can travel across entire ocean basins, reaching other individuals thousands of kilometers away. Dolphins and porpoises use echolocation, emitting high-frequency clicks and interpreting the returning echoes to build detailed acoustic images of their surroundings. Fish produce sounds by vibrating their swim bladders or grinding their teeth, signals that convey territorial information or attract mates. Even invertebrates, even shrimp, contribute to the ambient noise of the ocean, snapping their claws to produce sharp, percussive sounds that can stun prey or deter predators. In the deep ocean, where light does not penetrate and visibility is measured in meters at most, sound becomes the dominant way of perceiving space. Submersibles and remotely operated vehicles use sonar to map the seafloor and detect objects in the water column, sending out pulses of sound and measuring the time it takes for them to return. The data collected this way can be processed into images that resemble photographs, but they are not visual records. They are acoustic reconstructions, representations of how sound interacts with surfaces and volumes rather than how light reflects off them. The distinction matters because sound does not behave like light. It bends differently as it passes through layers of water with varying temperature and salinity. It reflects off objects at angles that depend on their density and shape. It can be absorbed or scattered by particles suspended in the water, by schools of fish, by layers of plankton. What you hear in the deep ocean is not a direct perception of the environment, but an interpretation, a translation of acoustic information into something the human brain can process, and like all translations, it involves loss and approximation. The deep ocean has its own acoustic structure, a layering of sound that varies with depth in ways that are not immediately intuitive. Near the surface, the water is relatively warm, and sound waves travel quickly. But as you descend and the water cools, the speed of sound decreases. At a certain depth, usually around 1,000 meters, the temperature stabilizes, and the speed of sound reaches a minimum. Below this point, pressure begins to dominate, and as pressure increases, sound speeds up again. The result is a layer in the ocean where sound waves slow down and then refract, bending back toward that layer rather than continuing straight. This creates a phenomenon known as the SOFAR channel, an acronym for sound fixing and ranging, a horizontal layer in the ocean where sound can travel for enormous distances with very little loss of energy. If you produce a sound within this channel, it will be trapped there, bouncing between the upper and lower boundaries of the layer, traveling thousands of kilometers before it finally dissipates. Whales have been using this channel for millions of years, likely without any awareness that they are exploiting a quirk of ocean acoustics, simply finding through evolution that calls made at a certain depth carry further than calls made elsewhere. Humans discovered the SOFAR channel during the Second World War and used it for submarine detection, for tracking underwater explosions, for communicating across ocean basins without the need for direct line of sight or surface vessels. The deep ocean, then, is not silent, but its soundscape is alien to human ears. It is a space where sound propagates in ways that have no terrestrial equivalent, where distance and direction become difficult to assess without instruments, where the distinction between near and far blurs into a confusion of echoes and refractions. A sound that seems close might have originated hundreds of kilometers away. A sound that seems directional might be the product of multiple reflections converging from different angles. Human ears are not adapted to interpret these signals. We rely on the way sound behaves in air, on the way it weakens predictably with distance, on the way our two ears can triangulate a source based on minute differences in timing and intensity. Underwater, especially in the deep ocean, those cues break down. Sound arrives from all directions at once, distorted by layers and currents, and the brain struggles to make sense of it. Divers report feeling disoriented by underwater sound, unable to determine where a noise is coming from, hearing things that seem to surround them rather than originate from a specific point. In the deep ocean, where there is no visual frame of reference to anchor perception, this disorientation would be total. Yet for the organisms that live there, this is not disorientation. It is simply the structure of their sensory world. They do not experience the deep ocean as confusing or alien because they have no memory of a different environment. Their brains process acoustic information in ways that make sense of the refraction and reflection, that extract meaning from patterns that would seem like noise to a terrestrial animal. Some deep-sea fish have lateral line systems, rows of sensory cells along their bodies, that detect minute changes in water pressure and movement, allowing them to sense the presence of other organisms even in complete darkness. Others have specialized organs that detect low-frequency vibrations, the kind produced by the movement of large bodies through water. These are not inferior substitutes for vision. They are different modes of perception, equally valid, equally effective within the context of the environment they evolved to interpret. The deep ocean is not a place where the senses fail. It is a place where different senses become primary. Humans, lacking these adaptations, must rely on technology to perceive what lies beyond the reach of light, and even then, what we perceive is mediated and incomplete. The abyssal plains, for all their emptiness, are not the only landscape the deep ocean contains. In certain locations, where tectonic plates pull apart and magma wells up from the Earth's mantle, the seafloor becomes geologically active in ways that create environments entirely unlike the cold, sediment-covered expanses that surround them. These are the mid-ocean ridges, underwater mountain ranges that stretch for tens of thousands of kilometers, encircling the planet like the seams on a baseball. They mark the places where new oceanic crust is formed, where molten rock emerges from below and solidifies into basalt, pushing the existing seafloor outward in a process that has been ongoing for hundreds of millions of years. The ridges are not smooth or uniform. They are fractured, faulted, interrupted by deep valleys and steep cliffs, and in places where seawater seeps down through cracks in the crust and encounters superheated rock, it is expelled back into the ocean as hydrothermal fluid, laden with dissolved minerals and heated to temperatures that can exceed 300 degrees Celsius. These vents, discovered only in the late 1970s, represent one of the most significant findings in the history of marine biology, not because they are rare or inaccessible, though they are both, but because they demonstrate that life in the deep ocean does not depend entirely on energy from the sun. The water that emerges from hydrothermal vents is black or white, depending on the minerals it contains, and it billows upward in plumes that look like smoke, giving the vents their common names, black smokers and white smokers. The fluid is chemically rich, containing hydrogen sulfide, methane, iron, manganese, and other compounds that are toxic to most surface-dwelling organisms, but serve as energy sources for bacteria that have evolved to metabolize them. These bacteria do not perform photosynthesis. They perform chemosynthesis, using chemical energy instead of light to convert carbon dioxide into organic molecules. This is not a minor variation on a theme. It is a fundamentally different biochemical pathway, one that allows life to exist in the complete absence of sunlight, independent of the photosynthetic food chain that supports almost every other ecosystem on Earth. The bacteria cluster around the vents in thick mats, white or yellow or orange depending on the species, and they form the base of a food web that includes organisms found nowhere else. Tube worms grow in dense colonies, their red plumes extending from white tubes that can reach lengths of more than 2 meters. They have no mouth, no digestive system, no way of ingesting food in the conventional sense. Instead, they house chemosynthetic bacteria inside their bodies, in a specialized organ called a trophosome, and they absorb the organic compounds the bacteria produce. The relationship is symbiotic and obligate. The worms provide the bacteria with access to both the chemicals from the vent and the oxygen from the surrounding seawater. The bacteria provide the worms with energy. Neither could survive without the other. Around the tube worms, other organisms gather. Clams and mussels cluster on the rocks, their shells encrusted with minerals, their tissues likewise hosting chemosynthetic bacteria. Crabs and shrimp scavenge and hunt, their populations sustained by the concentration of biomass that the vents support. Fish drift in and out, some of them residents, others transient visitors from the surrounding abyssal plains where food is scarce and energy is limited. The entire ecosystem exists in a small radius around the vent, confined to the area where the chemical-rich fluid mixes with oxygenated seawater, creating a gradient that organisms can exploit. Beyond this radius, the abyssal desert resumes. The vents are oases, but they are temporary ones. Hydrothermal activity shifts as tectonic forces move the crust, as magma chambers beneath the ridge cool or migrate. A vent that supports a thriving community today may go dormant tomorrow, and when it does, the organisms that depended on it must disperse or die. Larvae drift with the currents, searching for new vents, sometimes traveling hundreds of kilometers before finding a suitable site. The dispersal is inefficient, and many larvae never find another vent, but enough succeed that the communities persist across the entire ridge system, scattered and isolated, but connected by the occasional successful migration. The discovery of hydrothermal vent ecosystems changed the way scientists think about the limits of life. Before the 1970s, it was assumed that all ecosystems ultimately depended on the sun, either directly through photosynthesis or indirectly through the consumption of organisms that had photosynthesized. The deep ocean was understood to be sustained by the slow rain of organic matter from above, a derivative energy source that placed fundamental limits on how much life the deep could support. The existence of chemosynthetic ecosystems demonstrated that this assumption was incomplete. Life does not require sunlight. It requires energy, and energy can come from sources other than electromagnetic radiation. This realization has implications beyond Earth. If life can thrive in the complete darkness of the deep ocean, using chemical energy from geological processes, then it might also thrive in other environments previously considered uninhabitable, beneath the ice of Europa or Enceladus, in the subsurface oceans of distant moons, in places where sunlight has never reached but where geological activity provides an alternative energy source. The deep ocean, in this sense, is not just a remote part of Earth's biosphere. It is a model for what life might look like elsewhere, but even hydrothermal vents, for all their biological richness, represent only a tiny fraction of the deep sea floor. They are scattered along the mid-ocean ridges, separated by hundreds or thousands of kilometers of inactive crust, and they occupy a space measured in meters or tens of meters rather than kilometers. The vast majority of the deep ocean remains as it was before the vents were discovered, cold, dark, dependent on the slow descent of organic material from the surface, sparsely populated by organisms that have adapted to scarcity rather than abundance. The vents are exceptions, remarkable but not representative, and their existence does not change the fundamental character of the deep ocean as a place where energy is limited and life is patient. The ocean continues downward, past the ridges, past the plains, into regions where the seafloor itself begins to descend. Trenches form where tectonic plates converge, where one plate is forced beneath another in a process called subduction. The descending plate bends downward, creating a depression in the seafloor that can extend for thousands of kilometers in length and reach depths far greater than the surrounding abyssal plains. These are not cracks or fissures, but gradual slopes, the ocean floor curving downward at angles that are steep by geological standards, but often imperceptible to anything moving across them. A trench might descend at a rate of a few degrees per kilometer, a slope gentle enough that if you were walking across it on land, you might not notice the incline, but sustained over tens of kilometers, it produces a descent of several thousand meters. The trenches are the deepest parts of the ocean, the places where the seafloor reaches its maximum distance from the surface, and they represent less than 2% of the ocean's total area. They are narrow, elongated features, often located near the edges of ocean basins where oceanic crust meets continental crust, or where two oceanic plates interact. The Pacific Ocean contains most of them: the Mariana Trench, the Tonga Trench, the Philippine Trench, the Peru-Chile Trench. each a long, curved scar marking the boundary between converging plates. The transition from the abyssal plains to the trenches is not marked by any visible boundary, no line or barrier that announces the shift. The seafloor simply begins to slope downward more steeply, and the depth increases beyond 6,000 meters, the threshold that defines the Hadal zone. The name comes from Hades, the Greek underworld, a designation that reflects both the extreme depth and the early perception of these regions as unreachable and fundamentally hostile to life. The Hadal zone is not a single environment, but a collection of isolated trenches, each separated from the others by thousands of kilometers of shallower seafloor. Organisms that live in one trench cannot easily reach another. There is no continuous habitat connecting them, no corridor of deep water that allows migration between trenches. Each trench is an island, or more accurately, an inverted island, a depression surrounded by higher terrain, and the species that inhabit them have evolved in isolation, sometimes developing unique adaptations found nowhere else. The Hadal zone contains more distinct habitats than any other depth range in the ocean, not because it is large, but because it is fragmented. Pressure in the trenches exceeds anything encountered on the abyssal plains. At 6,000 meters, the pressure is approximately 600 atmospheres. At 8,000 meters, it is 800 atmospheres. At the deepest known point, the Challenger Deep in the Mariana Trench, the pressure reaches more than 1,000 atmospheres, equivalent to roughly 11,000 kilograms per square centimeter, or the weight of 3 large automobiles pressing down on an area the size of a fingernail. This is not a force that human technology can easily withstand. Submersibles designed to reach these depths require thick titanium or steel pressure hulls, reinforced viewports, and buoyancy systems capable of returning the vehicle to the surface even if all onboard systems fail. The margin for error is narrow. A small crack, a seal that fails, a viewport that weakens under repeated dives. Any of these can result in catastrophic implosion. Only a handful of crewed vehicles have ever reached the Challenger Deep, and each descent represents years of engineering effort and millions of dollars in investment. Remotely operated vehicles can go deeper more easily, but they are limited in their capabilities, tethered to surface ships by cables that can break or tangle, dependent on power and communication systems that can fail. The trenches are accessible in principle, but in practice, they remain among the least visited places on Earth. The sediment in the trenches is different from the sediment on the abyssal plains. On the plains, the sediment is fine and uniform, the product of steady accumulation over millions of years. In the trenches, the sediment is often coarser, mixed with material that has been carried down from the slopes above by underwater landslides or turbidity currents, dense flows of sediment-laden water that rush downhill and deposit their load at the bottom. The result is a more heterogeneous environment, with patches of soft sediment interspersed with areas of exposed rock or hardened clay. The bottom of a trench is not a uniform surface, but a complex landscape in miniature, shaped by processes that operate intermittently and unpredictably. Earthquakes are common along subduction zones, and the trenches are often seismically active, the ground shifting as the descending plate grinds past the overriding one. These shifts can trigger sediment flows, can collapse sections of the trench wall, can alter the shape of the seafloor in ways that take decades or centuries to stabilize. Life in the trenches was long assumed to be impossible, a reasonable assumption given the extreme pressure, the cold, the darkness, and the scarcity of food. Early oceanographers believed that the deep ocean was lifeless below a certain depth, that the combination of environmental stresses would eventually exceed the limits of biological adaptation. This belief persisted until the mid-20th century, when improved sampling techniques and deeper dives began to recover organisms from depths previously considered barren. The first samples from the Hadal zone contained amphipods, small crustaceans with segmented bodies and multiple legs, some of them reaching sizes far larger than their shallow water relatives. Later expeditions found fish, snailfish primarily, species with soft, gelatinous bodies and reduced skeletal structures, adapted to pressures that would kill most other vertebrates. These fish are not large. Most are less than 30 centimeters in length, but their presence at depths exceeding 8,000 meters demonstrates that vertebrate life can persist even in the most extreme conditions the ocean offers. They feed on amphipods and other small invertebrates, and they in turn are consumed by nothing as far as anyone knows, because there are no larger predators at these depths. They represent the top of a very short food chain, one that depends entirely on the detritus that drifts down from above, and the occasional carcasses of larger animals that sink to the bottom. The Huddle Zone is not rich in life by any measure, but it is not empty. And the fact that life exists there at all suggests that the limits of biological adaptation are wider than once imagined, that organisms can colonize environments that seem, from a human perspective, fundamentally incompatible with living processes. The Challenger Deep, located in the southern end of the Mariana Trench in the western Pacific Ocean, holds the distinction of being the deepest known point in the Earth's oceans. Its maximum depth is approximately 10,900 meters below sea level, though the exact figure varies slightly, depending on where and how it is measured, as the seafloor is not perfectly flat even at these extreme depths. The depression is roughly 11 kilometers long and oriented roughly east to west, a narrow slot within the larger trench system, and it represents the absolute lower limit of the ocean's vertical range. No naturally occurring point on the seafloor has been found that extends deeper. This does not mean that deeper points do not exist. Mapping of the ocean floor remains incomplete, and there are regions that have never been surveyed in sufficient detail to rule out the possibility of slightly greater depths. But based on current knowledge, the Challenger Deep is the farthest down you can go without leaving the ocean and entering the solid crust of the planet. Only a handful of crude descents have reached this depth. The first was in 1960, when the bathyscaphe Trieste carried Jacques Picard and Don Walsh to the bottom in a dive that lasted nearly 5 hours from surface to seafloor and back. They observed flat, featureless sediment and, briefly, a flatfish-like organism, though the identification has been questioned in later years and may have been an artifact of sediment disturbed by their descent. The second crude dive did not occur until 2012, more than 50 years later, when filmmaker James Cameron descended alone in the submersible deep-sea Challenger and spent several hours filming and collecting samples. Subsequent crude dives have been made by explorer Victor Vescovo in the submersible limiting factor, a vehicle designed for repeated deep dives and capable of carrying passengers. Each of these descents provided hours of observation time, video footage, and samples of sediment and organisms, but even cumulatively, they represent only a few dozen hours of direct human presence at the bottom of the Challenger Deep. The total time humans have spent at the deepest point in the ocean is less than a single day, and the area observed is vanishingly small, limited to whatever could be seen from the viewports or captured by cameras mounted on the submersibles, a radius of perhaps tens of meters illuminated against a surrounding darkness that extends for kilometers in all directions. What these dives have revealed is a seafloor that is neither barren nor dramatically populated, but somewhere in between. The sediment is soft and fine, easily disturbed by the movement of the submersibles, and it contains organic material that has drifted down from the surface, decomposed and processed by bacteria and other microorganisms during its descent. Amphipods are abundant relative to other visible organisms, scavenging on whatever food sources are available, and they have been observed congregating around bait deployed by remotely operated vehicles, appearing in large numbers within hours of the bait's arrival. Holothurians, sea cucumbers, crawl across the sediment, their movements slow and deliberate, and they leave trails behind them that can persist for days or weeks before being erased by the slow deposition of new sediment or the currents that occasionally move along the trench floor. Polychaete worms burrow into the sediment, and xenophyophores, single-celled organisms that grow to several centimeters in size, attach to rocks or sediment grains, their delicate structures visible in the light from submersible cameras. These organisms are not adapted to the Huddle Zone in the sense of being specially designed for it. They are adapted to deep-sea conditions in general, and they happen to be capable of tolerating the additional pressure and isolation that the trenches impose. There is no fundamentally different kind of life at the bottom of the Challenger Deep, no radically alien biochemistry or morphology. The organisms there are variations on themes that appear throughout the deep ocean, specialized but recognizable. The temperature at the bottom of the Challenger Deep is slightly above 1 degree Celsius, colder even than the abyssal plains, and it remains constant throughout the year, unaffected by seasonal changes at the surface or by weather patterns that influence the upper ocean. The water is nearly still, with currents so slow that they are difficult to measure, and the environment is one of profound stability. Nothing here changes quickly. Sediment accumulates at rates measured in fractions of a millimeter per year. Organisms grow slowly, reproduce infrequently, die and decompose over timescales that can extend for years. A carcass that sinks to the trench floor might be consumed over weeks or months, scavenged by amphipods and bacteria, broken down into components that can be reincorporated into the local food web. But the process is slow, constrained by the limited metabolic rates that the cold and pressure impose, and by the time the carcass is fully processed, the organisms that consumed it may have moved elsewhere or died themselves. The ecology of the Challenger Deep operates at a pace that is nearly geological, events unfolding over timescales that are difficult to observe or study within the duration of a single research expedition. The Challenger Deep is not the only deep point in the ocean, but it is the deepest one currently known, and it functions in the human imagination as a kind of conceptual terminus, the place where the ocean ends and something else begins. But the ocean does not end at the Challenger Deep. It continues horizontally, spreading across the trench floor, and it continues vertically as a column of water that extends from the sea floor to the surface, a distance of nearly 11 kilometers through which water molecules move. Pressure gradients establish themselves, and the physical and chemical properties of seawater vary in predictable ways. The Challenger Deep is simply the point where the seafloor reaches its maximum distance from the surface, and from the perspective of the ocean as a whole, it is not a boundary but a local minimum, significant in a geographical sense, but not a fundamental dividing line in the structure of the ocean itself. Still, it remains the deepest place we can point to, the farthest down the ocean goes, and in that sense, it holds a position that no other location can claim. The depth of the ocean is often expressed as a single number, a measurement that conveys how far down the seafloor lies, but this number does not capture what depth means as a physical experience or as a spatial volume. The ocean is not simply a surface with a distance beneath it. It is a three-dimensional mass of water, and depth represents the vertical extent of that mass, the accumulated weight of all the water above a given point. When you are at the bottom of the Challenger Deep, you're not just 11 kilometers down. You are beneath 11 kilometers of water, each cubic meter of which has mass and exerts force, and the sum of all that force is the pressure you experience. This is why pressure increases linearly with depth. It is simply the weight of the column of water above you, growing heavier with each additional meter you descend. The seafloor is not pressing down on you. The water is. The ocean at depth is not a void to be crossed, but a substance to be within, and the deeper you go, the more of that substance is above you, compressing everything below. Human perception of depth is shaped by experience on land, where vertical distances are limited by topography and the effects of elevation are subtle until you reach altitudes measured in thousands of meters. Even mountains, the tallest features on land, are dwarfed by the vertical extent of the ocean. Mount Everest, the highest point on Earth's surface, rises roughly 8,800 meters above sea level, but if you were to place it at the bottom of the Challenger Deep, its summit would still be more than 2,000 meters below the surface of the ocean. The Mariana Trench could contain Everest with room to spare, and this comparison, though frequently cited, remains difficult to internalize because it reverses the usual relationship between land and sea. We think of mountains as things that rise above the ocean, not things that would be submerged within it. And the reversal of that expectation creates a cognitive dissonance that numbers alone cannot resolve. The ocean's depth is not just a measurement. It is a negation of the altitude we associate with terrestrial geography, a descent into a space that has no visual or experiential analog on land. Mapping the ocean floor has been an ongoing effort for more than a century, but it remains incomplete in ways that are not widely appreciated. The majority of the seafloor has been mapped using satellite altimetry, a technique that measures subtle variations in the height of the ocean surface caused by the gravitational pull of underwater mountains, ridges, and trenches. These variations are tiny, measured in centimeters, but they can be detected by satellites and used to infer the shape of the seafloor beneath. The resolution of these maps is limited, however, typically around 1 to 5 kilometers, which means that features smaller than this, seamounts, canyons, individual volcanic cones, often go undetected. To map the seafloor in high resolution requires sonar, specifically multi-beam sonar systems mounted on ships, which send out pulses of sound and measure the time it takes for them to return after reflecting off the bottom. This produces detailed maps with resolutions as fine as tens of meters, but it is time-consuming and expensive, and only a small fraction of the ocean floor has been surveyed this way. Estimates vary, but most suggest that less than 25% of the seafloor has been mapped to high resolution, and in some regions, particularly the Southern Ocean and remote areas of the Pacific, the percentage is far lower. Large portions of the ocean floor have never been observed directly by any instrument, and the maps we have of those regions are approximations, interpolations, based on sparse data and general principles of seafloor spreading and tectonics. This means that the depth of the ocean in many places is known only approximately. The Challenger Deep is the deepest point we have measured, but there could be other points in other trenches that are equally deep or deeper, and we simply have not surveyed them with sufficient precision to know. The absence of evidence is not evidence of absence, and in the case of the ocean floor, the absence of detailed mapping means that much of the seafloor remains uncertain in its specifics. We know the general shape, the ridges, the plains, the major trenches, but the fine details, the local variations in depth, the locations of small features, these are often unknown. The ocean at depth is not a mystery in the sense of being fundamentally unknowable, but it is a mystery in the practical sense of being unobserved, and observation requires time, resources, and deliberate effort that has not yet been applied uniformly across the entire ocean. Even when the seafloor has been mapped, the map is not the territory. A sonar map shows the shape of the bottom, the contours and slopes and elevations, but it does not show what the bottom is made of, what lives there, how the environment changes over time. It is a static representation of a dynamic system, a snapshot taken at a single moment that may or may not reflect conditions at other times. The seafloor is not fixed. Sediment accumulates. Landslides occur. Organisms build structures, reefs, mounds, burrows, that alter the local topography. Tectonic forces shift the crust, opening new vents or closing old ones. The map becomes outdated the moment it is created, though the rate of change is so slow that for most practical purposes the map remains useful for years or decades. But useful is not the same as complete, and complete is not the same as understood. Understanding requires more than mapping. It requires observation, sampling, experimentation, the kind of sustained study that can reveal not just where things are, but how they function, how they interact, how they change. And this kind of study is difficult to conduct in the deep ocean, where access is limited, where the environment is hostile to instruments and humans alike, where each expedition represents a significant investment that yields only a small amount of data relative to the vastness of the area being studied. The deep ocean, then, is known in outline but not in detail, mapped but not comprehensively, visited but not inhabited, and the gap between what we know and what we could know remains large enough that new discoveries are still routine. The experience of descending into the deep ocean, even vicariously through video footage or descriptions, involves a progressive removal of reference points that the human brain relies on to orient itself in space. At the surface, orientation is clear. There is up, defined by the sky, and down, defined by the water below. There is light, direction, the movement of waves, the horizon as a distant boundary. These cues fade gradually as you descend. The surface becomes less visible, first as a bright ceiling, then as a diffuse glow, then as a faint suggestion of direction, and finally as nothing at all. The water around you, which was blue or green near the surface, shifts to darker shades until it becomes indistinguishable from the surrounding darkness. Your sense of motion becomes ambiguous. Are you sinking, Or is the water around you rising? Without visual landmarks, without the resistance of air or the pull of wind, the distinction becomes harder to maintain. Submersibles address this by providing instruments, depth gauges, altimeters, sonar displays, that translate position into numbers and images, giving the occupants a sense of where they are, even when their eyes can provide no useful information. But these instruments do not replicate the intuitive sense of place that vision provides. They offer data, not experience, and the mind must work to integrate that data into something that feels like spatial awareness. The descent itself takes hours. A submersible does not drop quickly through the water column, but sinks at a controlled rate, often 1 to 2 meters per second, a pace that allows systems to equalize and prevents damage from sudden pressure changes. At this speed, reaching the Challenger deep from the surface takes roughly 3 hours. 3 hours of steady sinking through darkness, with nothing to see except the occasional bioluminescent flash or the slow drift of marine snow illuminated briefly by the submersible's lights. The occupants sit in a pressurized sphere, the only part of the vehicle where human bodies can survive, and they watch through small viewports as the depth gauge counts upward. 1,000 meters, 2,000, 3,000. The numbers increase, but the view outside does not change in any proportional way. Darkness remains darkness. Cold remains cold. The only indication that you are moving deeper is the pressure reading, a number on a screen, and the faint sense that time is passing without any corresponding change in your surroundings. It is a form of travel that feels more like waiting than like motion, a suspension between departure and arrival that lacks the visual or kinetic feedback that usually accompanies a journey. When the seafloor finally comes into view, it does so suddenly, emerging from the darkness as the submersible's lights reach far enough to reflect off the sediment below. The lights create a cone of visibility, perhaps 10 or 20 meters in diameter, and within that cone the seafloor appears as it is, flat, soft, featureless in most places, occasionally interrupted by a rock or an organism. The rest of the trench floor extends beyond the lights, invisible, and the occupants must imagine it or trust the sonar to tell them its shape. Moving across the seafloor at this depth is slow and deliberate. The submersible hovers a few meters above the bottom, its thrusters adjusting constantly to maintain position against subtle currents, and it advances at speeds measured in centimeters per second. In an hour, you might traverse a few hundred meters, observing whatever happens to be within the narrow beam of light, sampling sediment or organisms if the submersible is equipped with manipulator arms, recording video that will later be analyzed for signs of life or geological activity. But the area you can observe is tiny, relative to the area that exists. The Mariana Trench is thousands of kilometers long, and the Challenger Deep alone is more than 10 kilometers across at its widest point. A few hundred meters of observation is nothing. It is a glimpse, a single frame in a film that has no beginning or end. Human presence at these depths is necessarily brief. Submersibles carry limited power, limited oxygen, limited supplies, and every hour spent at the bottom is an hour that must be balanced against the 3-hour ascent back to the surface. Most dives last no more than a few hours at depth before the vehicle must begin its return, ascending at the same controlled rate it descended. 3 more hours of darkness and waiting before the surface finally appears as a brightening overhead, then as a visible boundary, and then as air and light and the physical sensation of waves. The entire dive, from surface to seafloor and back, can take 10 hours or more, and the result is a data set that represents a single point in time, a single location, a single set of conditions that may or may not be representative of the trench as a whole. Repeat dives can provide additional data, but they are expensive and logistically complex, requiring support ships, specialized equipment, trained personnel, and the coordination of schedules, weather, and funding. Most trenches have been visited only a handful of times, and some have never been visited at all. Remotely operated vehicles can stay down longer, tethered to surface ships by cables that provide power and communication, and they can be deployed more frequently than crewed submersibles because they do not carry the risk or the life support requirements that human occupants impose. But they are limited in other ways. The tether restricts their range, and it can tangle or break if the vehicle moves too far or encounters obstacles. The cameras and sensors they carry are constrained by bandwidth, transmitting compressed images and limited data streams back to the ship, and the operators controlling them must work through a layer of mediation, watching screens and adjusting controls without the direct sensory feedback that being present would provide. Autonomous vehicles can operate without tethers, but they lack real-time control and must follow pre-programmed routes, collecting data that will not be examined until the vehicle returns to the surface. Each method of exploration has advantages and limitations, and none of them provides the kind of comprehensive, sustained observation that would be needed to truly understand the deep ocean in the way we understand terrestrial environments. The deep ocean, as a result, remains a place that is visited rather than inhabited, observed in fragments rather than continuously, known through instruments rather than through direct experience. Time in the deep ocean does not feel different from time anywhere else, because time is a constant, measured by the same physical processes regardless of location. But the rate at which observable change occurs does vary with depth, and in the deepest parts of the ocean, change happens so slowly that it becomes difficult to detect within the span of a human lifetime. A researcher who visits a site on the abyssal plain and returns a year later will likely see the same organisms in the same positions, the same trails in the sediment, the same rocks and features that were present before. The sediment will have accumulated by a fraction of a millimeter, imperceptible without instruments. The organisms will have aged, but their growth rates are so slow that the difference is not visible. A decade might pass, 2 decades, and the changes would still be subtle, detectable only through careful measurement and comparison of photographs. The deep ocean operates on geological time, or something close to it, and human observation operates on human time. And the mismatch between these two scales means that much of what happens in the deep ocean happens outside the window of direct observation. This has consequences for how we understand deep-sea ecosystems. Most of what we know about how ecosystems function comes from studies that track change over time. How populations grow and decline, how energy flows through food webs, how disturbances propagate and recovery occurs. But tracking change requires observing the same system repeatedly over a period long enough for change to manifest. And in the deep ocean, that period may extend beyond the duration of a research grant, beyond the career of an individual scientist, beyond the operational lifespan of the instruments being used. Long-term monitoring programs exist, some of them maintaining observation sites on the seafloor for years or even decades, but they are rare and expensive, and they can only cover a tiny fraction of the deep ocean's extent. Most of what we observe is snapshot data, single visits that provide a momentary view of a system, but no context for how it changes over time. We see the patterns but not the processes, the structures but not the dynamics, and we must infer the latter from the former, building models and hypotheses that may or may not reflect how the system actually operates. The organisms that live in the deep ocean have lifespans that are often longer than those of their shallow water relatives, another consequence of the slow metabolic rates that cold temperatures and limited food impose. Some deep-sea fish are thought to live for decades, possibly centuries, though aging them is difficult because the structures that typically record age, otoliths, vertebrae, grow so slowly that the annual rings are hard to distinguish. Deep-sea corals, which grow on seamounts and other hard substrates, can live for thousands of years, their skeletons accreting in layers that record centuries of ocean chemistry in their composition. These are among the oldest living organisms on Earth, and their longevity is not an exception, but a reflection of the environment they inhabit, where energy is scarce and growth is constrained by the availability of resources. A coral that grows a few millimeters per year will take centuries to reach a size that a shallow water coral might achieve in a decade, and if it is damaged or dies, the recovery of that structure, if it occurs at all, will take an equally long time. The deep ocean does not regenerate quickly. It does not recover quickly. It exists in a state of equilibrium that is stable not because it is resilient, but because it is slow, and any disruption to that equilibrium takes a long time to resolve. Human activity in the deep ocean is increasing, driven by interests in resource extraction, minerals, oil, gas, and by the expanding reach of fishing activities that now extend to depths that were inaccessible a few decades ago. Deep-sea trawling, in particular, has been identified as a source of significant disturbance, dragging heavy nets across the seafloor and removing not just target species, but also the habitat structures that support entire communities of organisms. The effects of this activity are difficult to assess because baseline data is often lacking, and the slow rate of recovery means that damage may persist for decades or centuries. A seamount that is trawled once may lose its coral cover, and that cover may never return. Or it may return so slowly that the process is invisible within any reasonable observation period. The deep ocean, for all its vastness, is not immune to human impact, and the impacts that do occur are likely to be long-lasting precisely because the systems affected operate on timescales that are incompatible with human planning horizons. There is also the question of what we cannot observe even in principle, not because the technology does not exist, but because the act of observation itself alters the system being observed. When a submersible descends to the seafloor and turns on its lights, it introduces a perturbation: light where there is normally none, motion where there is normally stillness, noise where there is normally only the faint ambient sounds of the ocean. Organisms may respond to these changes by fleeing, hiding, or behaving in ways they would not otherwise behave. And the result is that what we observe is not the unperturbed system, but a version of the system that has been influenced by our presence. This is not unique to the deep ocean. All observation involves some degree of interference, but in an environment where the natural conditions are so extreme and so stable, even a small perturbation can be significant. The light from a submersible may be orders of magnitude brighter than any bioluminescence an organism has ever encountered. The sound of thrusters may be louder than any natural sound in the environment. What we see during a dive may not be representative of what the environment is like when we are not there. And there is no way to verify this because the only way to observe the environment is to be present in it, and being present changes it. The deep ocean, in this sense, recedes not just from sight, but from the possibility of complete knowledge, not because it is fundamentally mysterious, but because it exists in a state that is partially inaccessible to the methods we use to understand it. The ocean is not just a surface feature of the planet, but a significant portion of its mass. Water covers roughly 71% of Earth's surface, and the total volume of the ocean is approximately 1.3 billion cubic kilometers, a number large enough to be nearly meaningless without context. If you were to collect all the water in the oceans and distribute it evenly across the entire surface of the Earth, the resulting layer would be roughly 2.5 kilometers deep, deeper than most of the continental crust is thick, deeper than the average elevation of land above current sea level. The ocean, in other words, is not a thin film stretched across the planet's surface, but a substantial mass, a reservoir that contains more than 97% of all the water on Earth. The remaining 3% is locked in ice, groundwater, lakes, rivers, and atmospheric vapor, and of that 3%, the vast majority is frozen in glaciers and ice sheets. The liquid fresh water that humans and most terrestrial life depend on represents a tiny fraction of the planet's total water budget, less than 1%, and it cycles through the atmosphere and terrestrial systems on timescales measured in days or years, while the ocean, which contains almost everything, cycles on timescales measured in centuries or millennia. The ocean is also a reservoir of heat, absorbing energy from the sun and redistributing it across the planet through currents that move water horizontally and vertically, mixing warm surface water with cold deep water in patterns that influence climate on regional and global scales. The heat capacity of water is high, meaning it takes a significant amount of energy to raise the temperature of a given volume of water, and this property makes the ocean an effective buffer against rapid temperature changes. Coastal regions experience more moderate climates than inland regions at similar latitudes because the ocean absorbs heat during the day and releases it at night during summer and winter, smoothing out the extremes that would otherwise occur. On longer timescales, the ocean absorbs heat from the atmosphere in ways that slow the rate of surface warming, a process that has been particularly significant in the context of recent increases in atmospheric carbon dioxide and the resulting changes in Earth's energy balance. The ocean has absorbed more than 90% of the excess heat trapped by greenhouse gases over the past several decades, storing it in the upper layers and gradually mixing it downward into the deeper ocean, where it will remain for centuries before eventually being released back to the atmosphere through the slow overturning of deep water currents. This absorption of heat has consequences that are not immediately visible, but are measurable and significant. The temperature of the upper ocean has increased by a fraction of a degree Celsius, a small change in absolute terms, but a large change relative to the stability that oceanic systems have maintained over thousands of years. Warmer water expands, occupying more volume than colder water, and this thermal expansion contributes to sea level rise, accounting for roughly 1/3 of the observed increase in global sea level over the past century. The rest comes from the melting of glaciers and ice sheets, which adds water to the ocean that was previously stored on land. But thermal expansion is significant because it represents a direct response of the ocean to warming, and it will continue as long as the ocean continues to absorb heat. The deep ocean has also warmed, though more slowly and by smaller amounts, because the mixing of heat from the surface to the deep ocean takes time, and the deeper you go, the longer it takes for temperature changes to propagate. Measurements of deep ocean temperature are sparse, limited by the difficulty of deploying instruments at great depths and maintaining them over long periods. But the data that does exist suggests that even the abyssal ocean is warming, though at rates measured in hundredths of a degree per decade, slow enough that it would be undetectable without precise instruments, but significant in the context of a system that has remained stable for millennia. The ocean also absorbs carbon dioxide from the atmosphere, a process that occurs when atmospheric CO2 dissolves in seawater and reacts with water molecules to form carbonic acid, which then dissociates into bicarbonate and carbonate ions. This chemical buffering has removed roughly 1/4 of the CO2 emitted by human activities since the Industrial Revolution, slowing the rate of atmospheric accumulation and the resulting warming. But it has also altered the chemistry of seawater in ways that are not neutral. The addition of carbonic acid lowers the pH of seawater, a process known as ocean acidification, and it reduces the concentration of carbonate ions, which many marine organisms use to build shells and skeletons. The effects of acidification are most pronounced in surface waters, where the exchange with the atmosphere is most rapid, but the changes propagate downward as surface water mixes with deeper layers, and over time, the entire ocean will be affected. The deep ocean, because it mixes slowly, will experience these changes more gradually, but it will experience them, and the organisms that live there, adapted to conditions that have been stable for thousands of years, may find themselves in an environment that is subtly but significantly different from the one their ancestors evolved in. The ocean, in this sense, is not separate from the rest of the planet's systems but deeply integrated with them, a dynamic component of the Earth system that responds to changes in the atmosphere, the cryosphere, the biosphere, and the lithosphere, and that in turn influences those systems through feedbacks that operate on multiple timescales. The depth of the ocean is not just a physical measurement, but a dimension along which these processes occur, and the deeper you go, the more insulated you are from short-term variability, and the more connected you are to long-term trends. The abyssal ocean and the Hadal trenches are the most stable environments on Earth, the places where conditions change the least on human timescales, but they are not unchanging, and the stability they exhibit is not immunity, but inertia, a slowness to respond that delays the manifestation of change but does not prevent it. The ocean absorbs and stores, mixing slowly, and what it stores remains for a long time, distributed across depths that most of the planet's surface systems will never directly interact with, but that nonetheless participate in the same planetary processes. The concept of depth implies a reference point, typically the surface, from which distance is measured downward. But for organisms that have evolved in the deep ocean and never ascend to shallower waters, depth has no meaning in this sense. They do not experience themselves as being at the bottom of anything. They simply exist in their environment, which is the only environment they know, and the distance to the surface is irrelevant to their biology or behavior. A fish living at 4,000 meters does not perceive itself as deep. It perceives water, pressure, darkness, the presence or absence of food, the chemical signals of other organisms, but not depth as an abstract category. Depth is a human construction, a way of organizing space that makes sense from the perspective of a surface-dwelling species, but has no corresponding reality for most of the organisms that inhabit the ocean. They do not move through depth zones the way a human might think of climbing or descending a mountain. They move through gradients of light, temperature, pressure, food availability, and these gradients do not always align neatly with vertical position. Some organisms migrate vertically on a daily basis, rising toward the surface at night to feed and descending to deeper, darker waters during the day to avoid predators. For them, depth is not a fixed location, but a variable dimension that changes with time and circumstance, and their navigation through it is guided by cues other than the distance from the surface. This raises a question about what depth represents outside the framework of human measurement. If it is not experienced by the organisms that live in the deep ocean, and if it is not a natural boundary that the ocean itself recognizes, then depth is primarily a human way of organizing and categorizing an environment that resists such organization. It is useful as a shorthand, a way to communicate where in the water column something is happening, but it does not capture the full dimensionality of the ocean or the ways in which different parts of the ocean are connected. Water moves vertically as well as horizontally, mixing layers that seem distinct when described in terms of depth, but that are part of a continuous system when described in terms of circulation and chemistry. Organisms move vertically, carrying energy and nutrients between layers, linking the surface and the deep in ways that a static depth profile does not convey. The ocean is not a stack of discrete zones but a continuous volume, and depth is just one axis along which conditions vary, no more fundamental than latitude or longitude, no more inherent to the system than any other coordinate. Still, the vertical dimension does have a directionality that the horizontal dimensions lack, because gravity imposes a structure on the ocean that is consistent and universal. Things fall downward. Energy flows downward, in the form of organic matter sinking from the sunlit surface to the dark depths. Waste products settle downward. Dead organisms sink downward unless they are consumed or decomposed before they reach the bottom. The ocean floor is, in a sense, the ultimate repository, the place where everything that is denser than water eventually accumulates. And this gives the vertical dimension a kind of finality that the horizontal dimensions do not have. You can move east or west indefinitely, circling the globe, but you cannot descend indefinitely. Eventually you reach the seafloor, and there is no further down to go. This finality gives depth a conceptual weight that is independent of whether organisms perceive it. The bottom is a boundary, a limit, and limits have significance even when they are not experienced directly. The deep ocean is also isolated in ways that shallow waters are not. Isolation in this context does not mean physical separation. The deep ocean is continuous with the surface ocean, connected by the same body of water. But functional separation, a lack of direct interaction or exchange on timescales that matter to individual organisms. A fish in the deep ocean will never encounter a fish from the surface. A plankton cell that sinks from the surface to the abyssal plains will not return. Energy flows downward but not upward, except in the form of the slow recycling of nutrients that eventually make their way back to the surface through upwelling, a process that can take hundreds or thousands of years. The deep ocean is a sink, not a source, and this gives it a character of remoteness that is not just spatial but temporal. What happens in the deep ocean happens in a context that is largely decoupled from the daily, seasonal, and even annual cycles that dominate life in the surface ocean. The deep ocean responds to longer cycles, to the overturning of ocean basins, to the slow drift of continents, to changes in Earth's orbit and climate that unfold over tens of thousands of years. It is not disconnected from the surface, but the connection is indirect, mediated by processes that operate so slowly that cause and effect become difficult to distinguish. This isolation also means that the deep ocean contains a record of the past in ways that the surface ocean does not. The sediment on the abyssal plains accumulates in layers that preserve information about the conditions under which it was deposited, the temperature of the water, the chemistry of the ocean, the abundance and types of organisms that lived in the surface waters above. Cores taken from the seafloor can be analyzed layer by layer, each layer corresponding to a different period in Earth's history. And the data extracted from these cores has been crucial to reconstructing past climates, understanding ice age cycles, and tracing the evolution of the ocean over millions of years. The deep ocean is not just a present environment, but an archive, a place where the past persists in physical form, and where the slow rate of change means that information is preserved rather than erased. Surface sediments are reworked by waves and currents, mixed by biological activity, buried and exposed by shifting shorelines. Deep-sea sediments, once deposited, remain largely undisturbed except by the slow bioturbation of burrowing organisms and the gradual compaction that turns sediment into rock. The deep ocean holds memory, not in the sense of conscious recollection, but in the sense of physical retention, and that memory extends back further than most terrestrial archives can reach. The depth of the ocean, then, is not just a measurement of distance but a marker of difference, a way of identifying regions that operate under different rules, at different paces, in response to different forces. There is a difference between knowing that something exists and experiencing its existence, between understanding a fact intellectually and encountering it in a way that engages the senses and produces a response that feels immediate rather than mediated. You can know that the ocean is 11 kilometers deep at its deepest point, can understand what that number represents in terms of pressure and distance, can calculate how long it would take to descend and what equipment would be required. But none of this knowledge is the same as being there, suspended in darkness with the weight of the ocean above you and the seafloor below. The only sound the hum of machinery and the occasional creak of the pressure hull, adjusting to stress. The deep ocean exists in a state that is primarily conceptual for most people, a space that is known through numbers and images and descriptions, but not through direct encounter, and this separation between knowledge and experience creates a kind of distance that is not just physical but perceptual. The deep ocean is real, but for the vast majority of humans, it is real in the same way that distant galaxies are real, or the interior of the Earth, acknowledged but not felt, understood but not internalized. This distance is not unique to the ocean. Most environments exist beyond the reach of individual experience. No single person can visit every forest, every desert, every mountain range, and yet we accept that these places exist and that their existence is not contingent on our having seen them. But the deep ocean occupies a position that is unusual in the degree to which it resists even the possibility of widespread direct observation. Forests can be walked through, deserts can be crossed, mountains can be climbed. The deep ocean can only be entered with substantial technological support, and even then only briefly, at great expense, by a small number of people. It is not accessible in the way that most terrestrial environments are accessible, and this inaccessibility reinforces the sense that it is fundamentally other, a realm that operates outside the sphere of normal human activity. The ocean's depth is not just a physical barrier, but a conceptual one, a boundary that separates the known from the mostly unknown, the observable from the largely inferred. The experience of depth, when it is experienced at all, involves a progressive dimming of the senses and a corresponding increase in reliance on instruments and indirect perception. You cannot see the deep ocean with your eyes except through the narrow cone of artificial light that a submersible casts. You cannot hear it with your ears except as vibrations transmitted through the hull. You cannot touch it directly because the pressure would kill you before you could register the sensation. What you experience is not the environment itself, but a mediated version of it, filtered through glass and metal and electronics, translated into forms that your senses can process: video screens, sonar readouts, temperature gauges, pressure dials. The instruments become your senses, and what you perceive is what the instruments tell you is there, not what is there in any unmediated way. This is true of all scientific observation to some extent, but in the deep ocean it is total. There is no fallback to direct perception, no moment when you can step outside and see for yourself. The environment is hostile in a way that leaves no room for unprotected human presence, and this means that human understanding of the deep ocean is entirely dependent on technology, on the ability to build machines that can go where we cannot, and report back what they find. But machines, for all their precision, do not experience environments the way organisms do. A camera records light, but it does not see. A sonar array detects echoes, but it does not hear. The data that instruments collect is accurate, within the limits of their design, but it is not experience. It is measurement, representation, a reduction of a complex environment to a set of numbers and images that can be transmitted, stored, analyzed. The deep ocean as perceived by humans is necessarily a simplified version of the deep ocean as it exists, stripped of dimensions that we cannot measure or do not think to measure, organized according to categories that make sense to us, but may not correspond to any natural division in the system itself. We observe temperature, pressure, salinity, light levels, the presence or absence of certain chemical compounds, the distribution of organisms. But these are the variables we have chosen to observe, the ones we have instruments for, and there may be other variables, other dimensions of the environment that we do not measure because we do not know they matter or because we lack the tools to detect them. The deep ocean that we know is a subset of the deep ocean that exists, and the relationship between the two is uncertain. This uncertainty is not a failure of science, but a recognition of its limits. Science does not claim to provide complete knowledge, only the best approximation available given the data and methods at hand. The deep ocean is studied with the tools we have, and those tools are sophisticated and capable, but they are finite, and the ocean is large and complex, and operates on scales that exceed the reach of individual research programs or even entire scientific disciplines. What we know about the deep ocean is substantial, built up over decades of patient observation and analysis, but it is not exhaustive, and it likely never will be. There is too much ocean, too much depth, too much variability, too many processes occurring simultaneously at scales from the molecular to the planetary, and any attempt to understand all of it in detail would require resources and time that are not available and may never be. The deep ocean will remain partially known, a system understood in outline, but not in every particular, and this partial knowledge is not a temporary state to be overcome, but a permanent condition to be acknowledged. The acknowledgement is not defeatist but realistic, an acceptance that some things exist beyond the full reach of observation, and that this does not diminish their reality or their significance, only our access to them. The fraction of the ocean floor that has been directly observed by human eyes or cameras is vanishingly small. If you were to add up all the time that all submersibles and remotely operated vehicles have spent on the deep seafloor, recording video and collecting samples, the total area covered would amount to something less than the area of a few city blocks, scattered across an expanse that covers more than half the surface of the planet. Most of the deep ocean has never been illuminated by artificial light. Most of it has never been photographed. Most of it has never had a human or a human-made instrument pass within 100 meters of it. This is not an exaggeration or a figure of speech, but a straightforward consequence of the logistical and economic realities of deep-sea exploration. The deep ocean is too large, too remote, too expensive to access, and the resources available to study it are limited. Every dive, every deployment of equipment, every research cruise represents a significant investment, and the return on that investment, in terms of area covered or data collected, is necessarily small relative to the size of the system being studied. The statistics are stark enough that they can create a kind of cognitive dissonance. We live on a planet that is mostly ocean, and most of that ocean is deep, and most of the deep ocean has never been seen. The maps that show the ocean floor, the ones that appear in textbooks and documentaries, are not based on direct observation, but on interpolation from sparse data points, on gravitational measurements made by satellites, on models that predict where ridges and trenches should be based on the movements of tectonic plates. These maps are useful, and they are mostly accurate in a general sense, but they are not comprehensive, and they contain gaps and uncertainties that are larger than the features they are trying to represent. A seamount might be missing from the map because it happens to lie between survey lines. A section of trench might be misrepresented because the sonar data is decades old and has not been updated. The map is a best guess, informed by science and refined over time, but it is not a complete record. This lack of comprehensive observation means that the deep ocean contains the possibility of the unknown in a way that most terrestrial environments no longer do. On land, satellite imagery provides near-complete coverage of the surface at resolutions fine enough to distinguish individual buildings, individual trees, sometimes individual vehicles. If something large exists on land, it is visible, and if it moves, it can be tracked. The ocean does not permit this kind of surveillance. Satellite sensors cannot penetrate water more than a few meters deep, and the resolution of satellite altimetry is too coarse to detect anything smaller than a large mountain. The deep ocean is opaque to remote sensing, accessible only through direct physical presence, and direct physical presence is rare. There could be features on the seafloor that have never been detected. Volcanic cones, landslide scars, unusual geological formations, and they would remain unknown until someone happens to pass near them with the right instruments. There could be species that have never been observed, populations that exist in regions no one has sampled, behaviors that occur only in the absence of human presence. The absence of evidence is not evidence of absence, and in the deep ocean, the absence of evidence is the norm. This does not mean that the deep ocean is full of undiscovered wonders in the dramatic sense that popular media sometimes suggests. It is not likely that there are large unknown animals lurking in the abyss, creatures that would revolutionize biology if discovered. The energetics of the deep ocean do not support large populations of large organisms, and anything large enough to be ecologically significant would leave traces, carcasses, bones, feeding signs that would eventually be encountered during the sampling that has occurred. The unknown in the deep ocean is more likely to be small, subtle, distributed, new species of invertebrates, new microbial communities, new patterns of distribution that do not conform to existing models. These discoveries are scientifically important, but they do not change the fundamental character of the deep ocean as a place where life is sparse, energy is limited, and change is slow. The unknowns are details within a larger framework that is reasonably well understood, refinements rather than revolutions. But the fact that the unknowns are details does not make them unimportant. Details matter, and in complex systems, small variations can have large consequences. A new species might reveal a metabolic pathway that was previously unknown. A new distribution pattern might suggest that deep-sea currents are more variable than models predict. A new behavior might indicate that organisms are responding to environmental changes in ways that were not anticipated. The deep ocean, despite being sparsely observed, is not static or fully characterized, and every new observation has the potential to reveal something that was not expected. This is both the challenge and the appeal of deep-sea research, the sense that the system is large enough and complex enough that there is always more to discover, always another question to ask, always another layer of detail that has not yet been resolved. The unknown is not a void, but a space filled with potential knowledge, and the boundary between the known and the unknown shifts incrementally with each new observation, each new data set, each new analysis. The deep ocean becomes less unknown over time, but it does so slowly, and the rate of discovery is limited by the rate at which we can deploy instruments and process data and integrate new findings into existing frameworks. The ocean is patient, and it does not reveal itself quickly, and those who study it must accept that the work is incremental, that understanding accumulates slowly, that any individual contribution is a small piece of a much larger puzzle that may never be fully completed. The vastness of the deep ocean is not just a physical property, but an epistemological one, a reminder that the limits of knowledge are not always set by the limits of theory or technique, but sometimes simply by the limits of access and time. The ocean continues in all directions, horizontally across basins and plains, vertically through the water column, temporally across millennia of slow change, and the depth we have been considering is only one dimension of a system that extends beyond the reach of complete description. The seafloor is not a destination but a boundary, the place where water meets rock and the vertical dimension terminates, and yet even there, at the deepest points we have found, the ocean is still present as mass and pressure and chemistry, still connected to the surface by the slow circulation of water and the steady drift of particles falling from above. The ocean does not begin at the surface and end at the bottom. It simply is, occupying space that was once air or land or something else, filling the low places on the planet's crust and responding to the forces that shape its motion and structure. The depth is a feature of that structure, a measurement we use to organize our understanding, but the ocean itself does not recognize the categories we impose on it. It exists as a continuum, and what we perceive as zones or boundaries are human constructs, useful but not inherent. Most of what lies below will never be observed in the way that we observe familiar environments. The darkness will remain unlit, the pressure will remain unrelieved, the cold will persist, the organisms that live there will continue their slow metabolisms, their patient waiting, their methods of survival that have been refined over millions of years in an environment that does not accommodate haste or excess. They do not require our observation to exist, and their existence is not diminished by our absence. The deep ocean functions without witnesses, has always functioned without witnesses, and will continue to do so regardless of whether we develop better instruments or allocate more resources to studying it. What we know is a small fraction of what is there, and what we will ever know will remain a small fraction, and this is not a failure but a condition, one that applies to most of the universe and is particularly pronounced in places that are difficult to access. The ocean at its deepest is not a mystery in the sense of something that invites solving. It is a mystery in the sense of something that resists complete transparency, that withholds aspects of itself, not out of intent, but out of the simple fact of its scale and remoteness. You can descend to the bottom and turn on a light and see sediment and organisms, and record what is visible, and all of that information is real and valuable. But it does not eliminate the surrounding darkness. The darkness remains, extending outward beyond the reach of the light, and it contains whatever it contains, unobserved and unobservable in that moment, and the only way to observe more of it is to move the light, which then illuminates a different small area and leaves the previous area dark again. The ocean is larger than the light, and it always will be. Perhaps this is what depth means finally. Not just distance measured downward, but a quality of being beyond easy access, a remoteness that is spatial and temporal and perceptual. The deep ocean recedes from human presence, not because it is hiding, but because it exists at scales and under conditions that human biology was not designed to encounter. We are surface creatures, adapted to air and moderate pressures and the presence of light, and when we venture into environments that do not provide these things, we do so provisionally, temporarily, with the understanding that we cannot stay. The ocean can be visited but not inhabited, observed but not fully known, mapped but not comprehensively, and these limits are not obstacles to be overcome, but realities to be accepted. The ocean is deep and it remains deep, and the depth is part of what it is. The water continues to press downward, the sediment continues to accumulate, the organisms continue their quiet existence, and all of it happens in a stillness that has persisted for longer than human history and will persist long after. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.